Do you guys know about this guy, Nate Silver? He's actually quite a good statistician. He doesn't hold any advanced degrees. He has a bachelor's degree in something or other, probably math. But he's taught himself to think like a statistician very well, and he does quite good Bayesian work. His models that have worked so well for the presidential and Senate and House elections and so on are essentially Bayesian hierarchical random effects models in which he takes the results from various polls and regards each poll as possessing a bias term of unknown magnitude and direction. And that's like putting in the bias term as a random effect in the model. And so he's doing modeling that's just like what we just did to produce his predictions for what's going to happen. And he seems just today to have done the same thing about the Oscars. So you can look at this at your leisure. He discovers from various sorts of previous signals, for example, what happened at the Screen Actors Guild and so on. He works out how well you can predict what happened at the Oscars over the past umpteen years from what happened at the Screen Actors Guild, for instance. And all of these things are potential predictors. And so he combines them in a Bayesian fashion and gets an overall composite predictor. And as a result, he predicts that Argo is going to win for Best Picture, and that Ben Affleck would have won for Best Director if he hadn't been snubbed. And so now it becomes according to these things, a pretty close contest between Spielberg, which I would have thought would have been a tremendous shoe-in, and Ang Lee for Life of Pi, maybe even Silver Linings Playbook. He's got Daniel Day-Lewis as a big favorite for Best Actor, which everybody probably agrees with. He's got Jennifer Lawrence as Best Actress, and on and on. So you can now, the thing that's great about people like this is that they put their predictions out there, and then we wait a little while and see what the truth is. And so he has an automatic feedback loop in almost everything he does. He predicts the presidential election, he predicts all the Senate races, he predicts all the House races, and he looks and sees. He makes a scorecard for himself, and when things don't work well, he goes back and changes the model until it works better. So he's something like a weather forecaster in that regard, in that he focuses on things that have a built-in feedback loop, and this is entirely admirable work. I think the guy is doing very good work. What do you got?
He was at Oculus at Google, so you can type in Nate Silver Oculus at Google if you want.
Cool. Yeah, the Signal and the Noise book is worth reading, actually. It's not very technical, and so those of you who have fully internalized what we're doing in this class will be frustrated. You're at a level now where you'll be frustrated reading this book because he's not writing to you. He's writing to people who are much less technical than you are, but you'll also see that his insights match the intuitions that we're using in this class, and that when you read his footnotes, you begin to get a little flavor of what he's actually doing, because he goes into more detail in the footnotes. So I commend him to you. He knows what he's doing by and large. All right, so here we are back with this Model 1, which is the two-independent sample Poisson model. So I'm going to go ahead and specify the model like usual, which should go swimmingly, I hope, and read in the data and compile and read in the inits. And it says everything's ready. So let's go ahead and do a sample. Pardon?
How does Nate Silver pick his prior?
He is probably tuning his priors based upon past success in a way that enables him to bring in the right amount of prior information with the right structure to create models that have retrospectively predicted well. And he's then hoping by a kind of extension of exchangeability judgment into the future that what's about to happen now will be a lot like what's happened in the past. So the specific details about how he specifies his priors he would regard as proprietary, I'm sure, and he is certainly not published on that. But I have a flavor, I have a pretty good idea of what he does, and if I were doing what he does, that's what I would do. From a Bayesian purely predictive point of view, you can regard both the sampling distribution and the prior as things that are tunable, as dials on the outside of a complicated box to produce good predictions. If your model isn't producing good predictions right now, then you're free to go back and change the model and change the prior until it does. And as long as you have holdout data that was not used in the modeling process, you always have a way to have a feedback loop where you compare what you thought was going to happen with what actually did happen. So it's not rocket science. So all right, so we'll do 1,000 updates, which are virtually instantaneous as our knee-jerk burn-in, and I will focus in on lambda.c. Some of what statisticians do in really complicated problems is sort of rocket science, and in fact, you'll see when we get into the Bayesian nonparametric stuff that there is certainly a rocket science level to what's going on there. But a lot of what people do is just common sense. Laplace said it himself back in 17-something or other. He said, statistics is common sense made numerical. That's basically what he said. So that's what we're trying to do. All right, so I've got my nodes in the graph defined. Winbugs here will work in a virtually instantaneous fashion because even though there's 500 some observations, based on what we learned earlier about the Poisson, is this a conjugate model structure? The gamma conjugate to the Poisson likelihood? It sure is. And so we have two independent samples, both with conjugate priors. And so we are not even doing Markov chain Monte Carlo. We're just doing ordinary IID Monte Carlo here. And so it's going to go just like lightning. And then all we're doing is creating a new column in the Monte Carlo data set effect, which is the difference of those two columns, lambda.c and lambda.e. And so watch how fast it goes. It's done. Less than 1 second, about half a second. Now, I started to ask you before we had a break. In fact, what do you expect to find? Do you expect to get answers, uncertainty bands that are narrower or wider than those from the Gaussian model? Also, do you expect to get point estimates that are similar to the Gaussian model? Or are the uncertainty bands going to be narrower or wider or about the same? What's your intuition? Under the Gaussian model, the sufficient statistic for the population mean is what? Sample mean. Under the Poisson model, the sufficient statistic for the underlying lambda, which is also the mean of the distribution, is what? Y bar, again. And so the point estimates should be identical, apart from Monte Carlo noise. But the uncertainty bands, do you expect the Poisson to produce wider or narrower uncertainty bands than the Gaussian? Some people said wider, some said narrower. Anybody want to advocate for wider? What's your thought?
Well, my thought is that it's Poisson in general has a longer tail.
Yes. Okay, but the tail has to be taken in relative terms in reference to the mean. So it's not immediately clear from just looking at the tail what would happen. Who wants to advocate for narrower? Why would the Poisson results be narrower, the intervals be narrower than those from the Gaussian? Pardon?
Better model.
A better model, but is it true that a better model always leads to narrower uncertainty bands? That turns out not to be true, and I'll give examples later on. Pardon? Yeah, that's right. The mean and the variance are the same. And so from an intuitive point of view, we can learn about the lambda at a faster rate because we get information about the lambda both from the first moment of the data and from the second moment. And so from that intuition, we expect the Poisson intervals to be narrower because we're learning about the parameter through the fact that the mean and the variance are the same. And another reason, I think I told you before, but there's been so many trees that you may not have remembered it, the Gaussian is the minimal Fisher information distribution for location. And so it's going to produce wider uncertainty bands than practically anything because that's built into, it's sort of baked into the Gaussian cake. So I expect narrower uncertainty bands for at least 2 reasons, and also at least 3 reasons, the other one being that I've seen this before. So let's have a go. So
that's using the data twice.
Yes, using the data twice, that's right. So here's lambda.c. What do you expect the autocorrelation function to look like? Given what I just told you about the sampling. Got to be white noise, and check it out. Completely white noise. Same for lambda.e. So what do you expect for the autocorrelation function for the effect, which is the difference of the two? Difference of 2 white noise processes has to be more white noise. So this was actually, as I said, Monte Carlo, not MCMC in this model. Okay, lambda.c. Obviously, the history is going to look perfect because it's just IID sampling from the posterior. I'm having trouble with Mr. Bill Gates here. Let's step out of the way. The posterior density looks sort of like a Gaussian, and the point estimate is exactly the same as before, but its standard error is actually noticeably smaller than what we got from the Gaussian, and that's for the reasons that I mentioned before. So let's go ahead and bring that down to 10 points. We have Monte Carlo errors, which are really Monte Carlo, not MCMC standard errors, on the order of 0.0002, if I did that right. And so these numbers with 100,000 iterations are pinned down pretty accurately. Then for lambda.e, we have also a Gaussian density, and it turns out also a mean that is more accurately estimated than in the Gaussian model. And so therefore you're going to expect that the difference, the thing called effect, is going to be produce a narrower interval as well. Here's your density for the effect. Here's your stats. We used to have a standard error from the Gaussian model of about 0.09. Now we're getting a standard error of about 0.077. So there you go. If the Poisson is a good model for your data, then the answer you get from the Gaussian modeling, and equivalently, as you said, the central limit theorem modeling, is worse. I mean, the Poisson answer's got to be better because the Poisson is able to take advantage of special information, namely that the location and scale parameters are the same, whereas the normal is set up to have two different degrees of freedom, one for location, one for scale. But did anything we just did with those MCMC diagnostics, like looking at the autocorrelation function or the quantiles, things like that, does any of that stuff check the validity of the model? No, unfortunately not. The MCMC diagnostics, these things like autocore and the quantiles and so on, they have nothing to say whatsoever about the quality of the model. They just talk about the quality of the mixing, the MCMC mixing. So we have not yet confronted this model with the possibility that it might be wrong. We've just said, we've just done something mathematical of the form, if the data really were Poisson, then you get a narrow interval. So far it's mathematics. It's not yet statistics because we have to check and see how the if is, whether it's reasonable or not. So let's go back now to the PDF. I've given you screenshots of how this goes, and I built a little table. Here's the little table. Comparison of inferential conclusions from models 0 and 1. This is on page 58 of part 4. And it's entirely appropriate to make a direct comparison between lambda c in the Poisson model and lambda, and rather mu sub c in the Gaussian model from a point estimate point of view, and even from other respects as well, because they are both representing estimates of the mean of each distribution in question. So notice that the column called posterior mean in the Gaussian Poisson, all the way down the page, they're virtually identical. As you go from the Gaussian model to the Poisson, you get exactly the same point estimates. But the uncertainty bands are sharply narrower from the Poisson. 0.0731 for the Gaussian on lambda c goes down to 0.0577. 0.0597 gets a little bit smaller to 0.0521. And on the thing we care about the most, the effect parameter, the 0.0944 from the Gaussian goes down to 0.0774. And when you make a little calculation, that works out. The posterior standard deviation for the treatment effect in the Poisson model is 22%. 22% larger in the Gaussian model than in the Poisson model. And the resulting interval, for the people who like to look at p-values and compare intervals with 0, the resulting interval from the Poisson story is comfortably all negative, and so 0 is no longer in the interval. So now we have some mathematics of the form, if the data are Gaussian, then the result with a two-sided story is not stat sig. If the data are Poisson, the result is they are stat sig. But so far, as I said, that's still just mathematics. However, although I did not emphasize it, there was already a clue right here in this table that the Poisson is not a good model for the data. Can anybody spot it? What's that? The ratio to variance. Yeah, variance to mean ratio. It's supposed to be what for the Poisson? 1. Take the standard deviation in the control group and square it. 1.24 squared is about 1.6. 1.6 divided by 0.944 is a variance to mean ratio of about 1.7, which is way different from 1. Similarly, 1.01 squared over 0.768 is about 1.3, 1.35. So we have actually right there in that summary table bald evidence right in front of us that the Poisson model is not very good because there's over-dispersion in the data with respect to the Poisson. We have extra, people say extra Poisson variation or extra Poisson variability. So to get a model that really works for the data, we have to work a bit harder. We're going to build a model that starts with the Poisson, but does something very natural from a scientific point of view that will produce a model that actually fits the data really well. I'm not going to show you today that the model fits really well because we're not yet up to the part of the material which we'll cover in part 5 of the course on things like model diagnostics, model comparison, things of that kind. That comes later. All right. Now, another thing that arises in basic modeling of this kind, when you have two groups that you're comparing, you have to decide between two possible ways of thinking about how to compare them. Any two numbers can be compared as long as neither one of them is 0. Any two numbers can be compared either in absolute terms or in relative terms. So I could compute like I did at the beginning. I could go y bar for experimental minus y bar for control. That's a so-called absolute difference. Or I could go y bar experimental minus y bar control divided by y bar control. That's a relative difference. Given that the data have some kind of Poisson character, at least given that the data values are all non-negative, and given that the rate parameter that we're interested in here is a number that has to be strictly positive, which seems more natural, the absolute comparison or the relative comparison? After all, if you take the difference of two lambdas, that number is capable of going negative, which is some sort of funny thing to be talking with respect to effects. Whereas if you take the relative difference between two lambdas, you always get a positive number. Right away, that makes me feel that the multiplicative model, which you get by focusing on relative change, is a better story for what's going on here than the additive model. And so,
why is that? Because I want to say the treatment group went to the hospital, right,
0.18 times
was negative.
Yes, that's true. Okay, so I'm going to try to say it better now. The difference model, the one we get by taking the difference of the two, has behind it, hidden behind it, a causal story that says the way you get someone's. Actually, let me draw a little picture for what's going on here. What I'm about to do is called the Neyman counterfactual model for causal inference. Have I ever talked about that in here before? Okay, so Neyman, and the name Don Rubin is associated with it also, but basically Neyman did it first. So I'm going to stick with Neyman counterfactual model for causal inference. Take the people in the experimental group. Here's person number 1. What would that person's number of hospitalizations have been if that person got in the experimental group? Is that something we know or don't know? No. We know that number. So number of hospitalizations if experimental, we know that number. And for this person, it might have been 2, for instance. But for someone who was in the experimental group, what would that person's number of hospitalizations have been if instead that person had been in the control group? Do we know that number? No. So number of hospitalizations if control is a question mark. And similarly, all the way down to however many people there were in the experimental group, 280, 285 or 287, whatever that number was, I think 285. So the last person might have been a 0, and there's a question mark. Now, in fact, I can put the whole thing into one big data set. Let's do it that way. So I'll just draw like that, and all these people here are experimental people. Now all the rest of the people are going to be control people. So for person number 286 all the way down to 572 or however many there were, Now these people are all control people. And so what would this person's, person 286, what would this person's number of hospitalizations have been if that person had been a control person? Well, we know that because that person was a control person. So maybe this is a 1. But now the pattern's reversed. It's a question mark over here. And in fact, all the numbers in this column are known down to maybe this last one is 0, and these are all question marks. So the numbers that we observe, the experimental people, the numbers in the experimental columns, those are called factual data. And similarly, the control numbers for the control people, those are also called factual data. But using a word that philosophers first thought about, the control numbers, what we would have seen for the control people if, for the experimental people, if instead they'd been control people, the philosophers call that counterfactual information because you didn't get to see it. It represents a what if, counterfactual. Basically, the idea behind counterfactual is a what if. And similarly, all these question marks over here are also counterfactual. This is a really useful way to think about causality because once you've set up the data in this fashion, you can begin thinking about how you would go about trying to estimate the counterfactual numbers from the factual numbers. If we randomize people to treatment and control, then that should make the control people similar to the treatment people on what their control numbers would have been. Do you buy that? So if I were to try to guess at the control, the question marks here in the experimental part of the data set, what would be, of the data we have here, what would be a good thing to use as a guess? You could use the observed control numbers as guesses for what the counterfactual control numbers would have been for the experimental people. So these numbers here become good guesses. This distribution becomes a good guess for this distribution. You can't say down at the individual person level what would happen, but you can say good guess for the distribution comes right from the factual part of things. And similarly, since the randomization occurred in this experiment, and we therefore again believe that the control and experimental people are similar, that means that the control people's experimental numbers, if we had been able to see them, should be similar to the experimental people's experimental numbers that we did get to see. So again, these numbers here should be a good guess, good estimate of the distribution down in the bottom part. That's one way to think about why it's so important to randomize to figure out what's going on from a cause and effect point of view. Because the randomization promotes comparability of the two groups, and that allows you to use the factual data to estimate the counterfactual data in both parts of the diagram where things are counterfactual. Really nice idea.
Different than exchangeability?
Well, exchangeability, having our uncertainty about all the numbers in this table, actually that's not true. Our uncertainty about all the control numbers ahead of time would have been exchangeable because of the randomization. And our uncertainty about all the experimental numbers in the table would have been exchangeable as well. But we would not have assumed exchangeability of the experimental column with the numbers in the control column unless we were prepared to believe before we even ran the experiment that what was true, that the experiment had no effect. And that's a stupid assumption to make because that's the whole point of running the experiment. So we would assume ahead of time, before any data arrived, we would assume conditional exchangeability of all the E numbers and all the C numbers, but not unconditional exchangeability of the two together.
But after you run the experiments, can I say that I am...
Yes, it's true. After I've run the experiment, I would say that because before running the experiment, the E numbers that I'm circling right now are exchangeable with the E numbers I'm circling right now. Now that the experiment's been run, the E numbers that I can see should be good predictors of the E numbers I can't see. So that's how you use exchangeability. It's a similar idea. That's right. We can't really talk about exchangeability of the E numbers that we've seen already with the ones we haven't because these numbers are known. And the exchangeability argument applies only to things that are unknown to you. You're trying to predict unknowns. Yep. Well, the problem with that idea is that, and this is the thing that you would call the basic dilemma of experimentation, is that by the very nature of how the experiment was conducted, is it ever physically possible to see both numbers for any one person? That would be like, that's right. Now that's different. This is a purely randomized trial. In a crossover trial, we could try running the same person over time under both the experimental condition and the control condition. And as long as you're willing to make an important and strong assumption of time homogeneity, then we actually get to see all the numbers in this table, not just half of them. So that's another way to think about how crossover trials work with respect to this diagram right here.
In the context of isolation.
Yes. If the only information we have about these people, the only covariate we have about these people is which people were experimental and which people were control, then the best thing we can do is to take the observed control numbers and use them as a good predictive guess for what the control distribution would have been like amongst the question marks, and similarly for the experimental numbers. That's the best you can do. Now, here's the question about additive versus multiplicative. What summary of the E and C numbers, if you could have seen them both, what summary of the E and C numbers would you find most natural? One idea would be to go E minus C, and the other one would be to go E minus C over C. So we could go E minus C, or we could go E minus C over C, and that's a little problem here because some of the control numbers are 0, so we'd have to think about what to do about that. But two different ways to think about how to summarize things. Let me tell you what the implied model is if you decided to focus on E minus C. That would be like saying that the E numbers are stochastically, and I'll say equal to with an ST sign over top of it, equal to the control numbers plus some delta. So that's like saying your model for what's going on here is that if you grab the control people and put them in the experiment, that would have caused whatever their control hospitalization number would have been to go up or down in an additive fashion by the amount delta. And everybody, according to this model, would have the same delta, and it would correspond to the average change, right? Does that make sense to you as a model for what's going on here? Well, if your control number was 0 and the delta was negative, you'd be predicting a negative number for the E number. That doesn't make sense. And you're right, some people are sicker than others, but we don't have any information about that yet. We're going to do something in a minute that proxies for that fact. But for now, all I'm saying is that this is not really a very good model for what's going on, because if your control number was 0 and the delta is negative, as we see it is in the data set here, then your experimental predicted number would be negative, and that doesn't make any sense.
You can't put a greater than or equal to 0.
No, what we're saying stochastically is apart from noise, E equals C plus delta. You're right, we could put a noise term on that might, and hope the noise term was big enough to make this number be positive, but the noise terms they tend to be mean 0, and so sometimes that makes things even worse, right? So this is not reasonable, actually. What we've done so far was an easy thing to do, but it's not really reasonable. What would a different formulation say, which would make sure that everything stayed positive, all the data, at least the data stayed non-negative? Let's try a different one. So this is a formulation that's called an additive model for the data. What if we tried instead the idea that the way you would get the experimental number would be to take the control number and multiply by something instead? For instance, some number like 1 plus a delta, which could be either positive or negative. Then that would be what people call a multiplicative model. This one here. And as long as the delta was smaller than 1 in a negative way, and it is going to turn out to be smaller than 1 in a negative way, think of it as a number like minus 0.18 or so, for instance, or minus 0.19, something like that. Then this model says that whatever your control number would have been, whatever number that would have been, the experimental number would be about 80% of that number as a relative thing, because 1 minus 0.18 is about 80%. And so this is saying that the treatment has a multiplicative effect. It takes whatever anybody's hospitalizations would have been, and it multiplies them by a number less than 1. And that's okay for 0, because 0 times this thing is still 0.
So don't you run into the same problem? If my delta on the second one is too small, then suddenly E is negative.
If delta is less than 1, I'm sorry, if delta is greater than -1, then this whole thing is off, right? But if delta is some modest negative number, then this is actually a pretty good description of what's going on, and it forces things to have the property that the E numbers never go negative. So as long as delta is some number not too far from 0, either on the positive or negative side, this makes pretty good sense as a kind of a first-order approximation about what we think is going on. Now, really, what is going on is that the way you get from some person's control number to that same person's experimental number is you multiply by 1 plus delta for that person, right? That's really the kind of model we really like to fit. We'd like to go, the person's I's control number should be the same as their experimental number times 1 plus delta I. We'd like to have everybody have their own chance to have a different delta because some people, as you pointed out, are sicker than others, some are older than others, and so on. But we can't fit that model directly because it has too many parameters. Same problem as before. Here we'd have 572 observations and 572 parameters. So this is what we'd like to do, but we can't. So I'm going to go ahead and cross through those little guys because we can't fit them. But now returning to the PDF. Okay, so I mentioned this already. So the reason that the Poisson model is sharper in its uncertainty bands is when a location parameter is the only thing at issue, the Gaussian is a kind of conservative choice, and also we get second moment information to help. Both the Gaussian and Poisson models that we looked at so far implicitly assume that the treatment effect is additive, where equal stochastically means is stochastically equals to. In other words, apart from random variation, the effect of the IHGA intervention is to add or subtract a constant to or from each person's hospitalization underlying rate. However, since the outcome variable is non-negative, it's plausible that a better model for the data would have a multiplicative history. And so here people call this a multiplicative model, equation 37. In other words, apart from random variation, the effect of the IHGA intervention is to multiply each person's underlying propensity to become hospitalized by a constant that's somewhat a little bit bigger than 1 or a little smaller than 1. And you can make a QQ plot of the control and experimental outcome values, and sometimes that picture can show you what's going on. So by a quantile plot, I mean the following. If you sort the control numbers and put them on one axis, and you sort the experimental numbers and you put them on the other axis, and if the sample sizes were exactly equal, you line the sorted numbers up against each other, and if they're not, you do a little bit of interpolation to the quantiles to see what they would have been if the sample sizes had been equal. Suppose, so this is a QQ plot, as it's called, quantile plot of the control numbers against the experimental numbers. Suppose that the treatment had no effect at all. Then what should this picture look like? Suppose the effect of the experimental intervention was identical to the control, then it has to look like what? The 45-degree line, not just a straight line. It has to look like the 45-degree line, right? And so this is the line in this picture that corresponds to no effect. Everybody buy that? Now, what if the treatment had an additive effect? What if the treatment added a constant to everybody? Then how would that show up in this picture? The line would have the same slope, but what would happen? The line would be what? It would be vertically shifted with the same slope. It would still have slope 1, but now it would look like this if there was an additive effect. And that discrepancy there would be the delta in the additive effect. So that's what the additive effect would look like if the effect really were additive. Instead, suppose you make the same picture, and this is again the no effect story. This is the line E equals C, or Y equals X. Suppose, once again, this time now, suppose that the effect was multiplicative. Then how would that show up? It would no longer be just an additive up or down. What would it do? It would take this line here and shift the slope, right? It would still go through the point 0, 0, but the slope would be bigger or smaller than 1, according to whether the effect was to make things bigger or smaller. So what would happen with a multiplicative effect is it would still be a line that went through the origin, in the same way that this one still had the same slope of 1 but changed the offset, as you could say. Here, the thing that's the same is that both lines would go through 0, but this one would have a smaller or larger slope. So again, this is the no effect line. And the picture would look like that if the effect were multiplicative. So it is sometimes possible to make one of these QQ plots and look at it and see, do the data look like a straight line with slope 1 but higher or lower than the y equals x line, or does it look like a straight line but with slope bigger or smaller than the slope 1 for E equals C but going through the origin. And unfortunately, sometimes the effect is partly multiplicative and partly additive, in which case what you get is this wacky thing where here's the no effect line, and the actual line you get is something that looks sort of like that, where both the intercept is different from 0 and also the slope is different. So this would be a mixed additive dash or slash multiplicative effect. If you get a straight line at all, that happens more often than you would like. Here, unfortunately, when you try to make that picture, you discover that it gives you no information, and that's because the Poisson story, actually it's because essentially this is what the picture looks like. Oh, I'm sorry, switch back. So I plotted the E versus the C values in a QQ plot fashion with the radii of the plotted circles proportional to the number of observations, because we have a whole lot of ties in this data set. And the solid line corresponds to no treatment effect, the small dotted line to the best fitting multiplicative model, and the large dotted line to the best fitting additive model. And it's actually impossible to tell which of those two is a better summary of the data here. And the reason is essentially that the Poisson model has only one parameter for both location and scale. The multiplicative and additive formulations fit equally well. So you can't, in this model, use that picture to help distinguish between the two possibilities. But I'm going to rephrase the data in terms of the multiplicative model because it generalizes better to where we're headed in the hierarchical representation we're about to use. So let's see how to do that. A simple way to write the multiplicative model is to do something that you were probably taught back in Statistics 1 when you took it yourself, namely the following. So when you have two independent samples data, one way to visualize that data is you have a vector of experimental numbers and possibly a vector of control numbers of potentially different length than that, and you just have these two columns of numbers, right? But another way to visualize it is to put all the experimental and control numbers into one big column and call it Y. So all the E numbers are in here along with all the C numbers. For instance, in this one here, I might put all the E numbers there and all the C numbers there. However, if all I told you was that I just took all the E and C numbers and I stacked them together into a big vector and I didn't tell you where the dividing line was, you couldn't analyze the data anymore. So if we're going to write the Y, the outcome variable in this way, we have to add an X that helps us to distinguish. And what role would the X have? 1 if one of them and 0 if the other. And we might as well take 1 if experimental and 0 if control. So do you buy that? An alternative way to summarize the two independent samples data structure is with a regression structure in which the outcome variable is for everybody is all in one big data set. And here the sample size, the overall sample size, is the whole, in this case, data set 572. Here we had, what was it, 280, 285, and 287. But now we have, this is actually a somewhat more satisfying way to write the data because we have everything under one rubric. We got one model for the whole data set rather than two parallel models for the data. And would you agree that these two formulations are equivalent? Do they involve the same exact information being conveyed? If I gave you this formulation over here on the left, could you reconstruct the one on the right? Perfectly. If I gave you the one on the right, could you reconstruct the one on the left? Perfectly. And so they are identical representations of the same data, but the one on the right turns out to be a better way to think about the data we're working with here. So returning now to the PDF. Why would there be no signal? I'm returning now to the nothing at all.
Your monitor disappeared.
Oh, you've got it here, but my monitor disappeared. That's funny. So press again. You guys get to see no signal. Wait. You guys get to see the right thing, but my monitor's gone dead. So that's not the end of the world. I can keep talking and just look at the screen and hope you guys and look back over my shoulders. Okay. So a simple way to write the multiplicative model is to re-express the data in the form of a regression of the outcome variable y, namely number of hospitalizations, on an indicator or dummy variable, like we said. We'll put in the x's to be 1 if you're a treatment person or experimental person, and then 0 if not. So writing the data the way I did a minute ago, but expressing it horizontally rather than vertically to use less space on the page, I have I running from 1 to 572, and in the first 287 people, all of those people are control people, and so we don't want that. And we have the y's that go along with them, and then all of the remaining people, 288 through 572, those are all experimental people, and so we have the y's that go for them.
VC Ops, do you still see us?
I can see the room, but I'm not seeing the slides or the laptop.
That's not good.
All right, I'm working on it. Can you guide me through? Should I do the video conferencing screen?
Yeah. Oh, I see it now.
All right, our internal monitors aren't working. Are the monitors in the back? They're not working either. All right, so
let's see.
You can see it now, VC Ops?
Yes, I can see it.
Okay.
Are you guys in the back of the room? Have you been focusing mainly on your own monitors, or are you able to see the front? One idea would be to keep going until the next break and then try to fix it during the next break. The next break is in about 15 minutes, so is that okay? We'll keep going for now and fix it during the break? Okay. Now, watch the following cool thing. Now we are able to finally do something with this regression structure that is just what we want from a scientific point of view, at least on the first line of the model. The first line of the model now says, if you knew what that person's lambda I was, their underlying propensity to become hospitalized, then their observed number of hospitalizations, yi, would be like a draw from a Poisson with that person's lambda. And then all the yi's are independent. So this is great because it goes toward that goal we've been talking about, trying to get close to all course long, in which everybody is allowed to have their own parameter because everybody's different with respect to these confounding factors like how old they are and how sick they are at the baseline of the experiment and so on. But we've also agreed that as desirable as this model is from scientific grounds, it can't be possibly estimated. Why not? Yeah, or equivalently too many parameters. We have 572 data points and 572 parameters. The best you could do in this model, either from a frequentist or Bayesian point of view, is if the yi was 0, you'd estimate the lambda to be 0. If the yi was 2, you'd estimate the lambda to be 2, and so on. That's not a very interesting story. So somehow we have to do dimensionality reduction down from 572 parameters to a smaller number of parameters that captures what's going on. And the rewriting the two independent samples Poisson model in a multiplicative fashion, we can do that by means of the second line that I'm going to show you now. So let's look at what's going on here. I would like to bring in a regression structure in which the lambdas depend upon which group the person is in, because that's the only information I have about them. So what does a regression function look like involving a variable x? The simplest form of a regression function is a constant plus a slope times the x variable. So an intercept plus the slope times the x. So the right-hand side of the middle equation in the middle line of equation 38 says, okay, I'm going to go gamma 0 plus gamma 1 times xi. I could have used an alpha and a beta or some other notation, but I'll just use gamma 0 and gamma 1. And you might think originally that what you'd want to write down is, well, why not having the lambda I equals gamma 0 plus gamma 1 times xi. So the first line of the model says, says yi given lambda I are independently Poisson and everybody has their own lambda. But that's too many parameters. So let's try a little regression structure like we did, notice, like we did with the story involving the teacher expectancy study, where now instead of the X being at the level of the study, it's actually at the level of the individual person in the IHGA experiment. What is wrong with writing down just lambda I equals gamma 0 plus gamma 1 xi? What could go wrong with that? Pardon? Well, but it's additive on the lambda scale. You're right. It doesn't have the right multiplicative structure yet. You're right. But there's a technical thing that jumps out even more strongly than that. The x's are either 1s or 0s. These are regression parameters, gamma 0 and gamma 1. In a regression problem, where can the gamma 0 and the gamma 1 live? Do they have restrictions on them, or could they be anywhere they want on the number line? They could be anywhere you want. So the right-hand side of this equation lives anywhere it wants on the whole real line. But the lambdas have to live where? They have to be strictly positive. And so we have to make something, do something to either the right-hand side or the left-hand side to make them conform with respect to where they live. And what's the simplest thing you could do to something that's strictly positive to make it live on the whole real line? Take its log. And so that's how we get the multiplicative model. That's a simple way to motivate the multiplicative model. What it says is, everybody starts out having their own lambda, but that's too many parameters. So now let's take log lambda I and regress that on the indicator variable, the dummy or indicator variable for which group you're in. Now with line 1 and 2 together, how many parameters do we have? Line 1 by itself, we had 572 parameters, but when you add line 2, you're left with how many parameters? The lambdas just act like carriers, and so there are only 2 parameters in this model at the moment, namely the gamma 0 and the gamma 1, because the x's are known. As soon as I told you the gamma 0 and the gamma 1, you could work out the log lambdas and exponentiate them to get the lambdas, and so you'd be done fitting the model. So actually this model has gone down from 572 parameters to 2 parameters, and then we put a diffuse prior on the gamma 0 and the gamma 1, representing the fact that we don't know much about how this should go. But actually, if you think about it, the 2 independent samples Poisson model had how many parameters? 2. Also, there was 1 lambda for the control group and 1 different lambda for the experimental group. So actually, I'm about to show you now that this model, this representation, has the same information content as the previous model did, as follows. Because let's think about it. In this model, the control people have log lambda I equals their gamma 0 plus their gamma 1 times 0, because those people all have x equals 0, so that's just gamma 0. Now exponentiate both sides. Those people all have their lambda I equal to e to the gamma 0. And let's just call that the lambda for the control condition, because that's the name we had for it before. So there's a direct relationship between our previous parameterization. Lambda c stands for the overall mean in the control group, and it's just e to the gamma 0 in this new model here. And now what happens in this model, the treatment people, or experimental people, all have their log lambda equal to gamma 0 plus gamma 1 times 1, which is gamma 0 plus gamma 1. And now let's exponentiate both sides, and so that means that all of the experimental people have the same lambda, namely lambda dot e, or lambda e is what we called it before, but that's just e to the gamma 0 plus gamma 1. And that in turn is e to the gamma 0 times e to the gamma 1. And look, that's where the multiplicative thing is happening. Because look, that now we have it expressed as lambda e is equal to lambda c times e to the gamma 1. There's the multiplicative effect. And in fact, does anybody remember what the Taylor series is for e to the x? 1 plus x. The first two terms are 1 plus x. And so for basic Taylor series, that for gamma 1 not too far from 0, e to the gamma 1 is like 1 plus gamma 1. And so what that means is that this new model, equation 40, for gamma 1s that are fairly near 0, we have lambda e being approximately equal to 1 plus gamma 1 times lambda c. And that's exactly the thing we were trying to convey with the idea of a multiplicative model. So pretty cool. This is a way to write the Poisson, two independent samples Poisson model in multiplicative terms instead of in additive terms. Now, it's easy to fit this model. In fact, I'm just going to go ahead and kill off this entire thing and start a new WinBugs. You go back to the course web page and look down again. We have something called ihga-model2.txt. And I'll grab that and stick it inside WinBugs. And look at how the model expresses just what we said. Now, instead of having two independent parallel for loops, one for the control people and one for the treatment people, we have one big for loop for everybody. So that's expressing the data in a regression structure. And the model looks like this. If you knew what someone's lambda I was, the yi would be a draw from a Poisson with rate lambda I. And then we've got that the log of the lambda I is assigned the value of gamma 0 plus gamma 1 times x of I, just like we wrote down a minute ago. Now I'm using a syntax trick in WinBugs that should not strictly be part of their language, but they've allowed this. Basically, you would have thought that the only thing you're allowed to do is to assign something like lambda I a particular value, not log of lambda I. So this is sort of a compound statement where it says log of lambda I is assigned this thing rather than some other thing like eta sub I or whatever. But this is a compound structure that's perfectly allowed in the WinBugs framework, and that's because it's so natural all the time to take log of parameters that are strictly positive, for instance.
That's
So,
weird because before our sigma thing, it didn't predict that.
That's right. But here, this is one special, they made a special exception for this because it comes up so often in modeling that you're working with something that lives on a parameter that lives on the positive part of the real line. You're going to want to hit it with a log. Now, the only free parameters in this model are gamma 0 and gamma 1. But now they're regression parameters, and they can live anywhere they want on the real line. So why not give them normal priors with mean 0 and small precision? And I could easily have used 1.0 e minus 6 here instead of 1.0 e minus 4 like I did before. I don't know why I used minus 4. But that means that the precision is 0.0001, which means that the variance is 10,000, and therefore the standard deviation is 100. So this is like saying that gamma 0 could be anywhere from minus 300 to plus 300, and so same for gamma 1. And you will find that when we look at the actual range in which the likelihood is appreciable, that's a really flat prior. So this is fine. And now I have the derived quantities down here at the bottom. We know from the little work that we just did a minute ago that lambda c is a derived quantity equal to e to the gamma 0. And lambda dot e is a derived quantity equal to e to the gamma 0 plus gamma 1. And I can create something called multiplicative dot effect, which is just e to the gamma 1. So those are exactly the same quantities we just worked out by just thinking about things algebraically. Now let's get the data. Data is even bigger file than it was when we only wrote the data in a two independent samples form, because we have to have a regression structure where there's a vector of y numbers of length 572 length and a vector of x numbers also of length 572. So I'll just grab those guys and put them into a new data file. So this is a bigger data set than before, but so what? I mean, we can certainly work with it. I'll show you later on in the course an example, as I said, where the data vector has, the y vector has 70,000 observations in it, and each of the x1, x2, x3 vectors has 70,000 observations in it. And WinBugs has no trouble syntactically working with data like that. It just takes a long time unless you parallelize. Okay, now what about initial values? Well, let's see what we got back here. So IHDA inits -2. Here I'm going to give it generic starting values. I'll just use 0 and 0 for each one because they live anywhere they want on the real line. So why not just start them at the place that's in the middle on the real line. All right, so we're ready to do some fitting. So here's the model specification tool, and I'll check the model, and it's fine. And I'll read in the data, and it's fine. And I'll compile, and everything's fine. Bugs, and I'll read in the inits, and everybody's happy. So I'll get rid of the specification tool and do a kind of knee-jerk update of 1,000 for burn-in, which is probably not really necessary. You'll notice that things move more slowly now because it has 572 observations in the data set. So the regression structure actually causes the MCMC to move a little more slowly, but that's okay because it proves to be exactly the right way to look at the data to generalize properly to describe the extra Poisson variability, which we know is present in the data. So gamma 0, gamma 1, then all those guys at the bottom that are interesting to look at, lambda.c, and lambda.e, and mult.effect. All right, now let's get ourselves the usual 100,000 updates with a refresh every 1,000. And now this is taking a while, and it's going to take about 1.5 minutes or 2 minutes because even though there aren't that many, there are only 2 parameters in the model, it's got to, in effect, it has to create, if you look at what it's doing, every single time it updates gamma 0 and gamma 1, it has to create a new lambda I. So there's a gamma 0 column in this MCMC data set and a gamma 1 column, and there are 572 lambda columns. And it has to keep updating them every time you get a new gamma 0 and a gamma 1. So the MCMC data set has a lot more columns in it than it did before when we expressed things in this parameterization, so no wonder it takes longer. So we have 1 minute or 2 before the break. We could either break now and come back later, or you could, anybody has any questions or comments, we could have a go at them for 1 minute or 2 while we're waiting for the updates. Anything on anybody's mind? Well, let me ask you this. How do you expect the results from this model to compare with the results from the additive model? Let's look back at the I certainly expect that also. Let's now go back and I'll remind you of the 2 different models. In fact, I'll show you how the new model relates to the old one. So reminding you of what's going on here. Lambda C in the old model is exactly the same as e to the gamma 0 in this model. Lambda E in this model, in the old model, is exactly the same as lambda C times e to the gamma 1. And so the inference for lambda C and the inference for lambda E in this model should be what? In relation to the old one. Identical, absolutely identical. The only difference is that we're not going to focus on lambda E minus lambda C. We're going to focus on the ratio lambda E over lambda C to look at the multiplicative effect. And so we'll focus on e to the gamma 1, but that's going to be a lot like 1 plus gamma 1, and it's going to turn out that the multiplicative parameter written on the 1 plus blah blah scale is going to be quite close to the additive parameter because both of them represent deviations from 0 in the additive case or 1 in the multiplicative case that are not very big. And so it's going to turn out, interestingly, even though the model's written in a completely different way, that the results, although they're not directly comparable because they're on slightly different scales, additive versus multiplicative, are quite similar. Let's take our 3:45 break and come back and see the comparison.